Welcome back to the lectures on chemistry and introduction to molecular spectroscopy. In this short lecture, we shall examine the microwave spectra of polyatomic molecules, again subject to the rigid molecular approximation. Spectra of symmetric top molecules are the first region in which we start getting more and more details from microwave spectra regarding the structures and so on, but you would be surprised to see some patterns of symmetric top being very similar or identical to the pattern of the spectra of diatomic molecules. Now, please recall that we always take the rotational kinetic energy, and the rotational kinetic energy when the moments of inertia are all identical is given by the angular momentum squared divided by the moment of inertia. However, if a molecule is such that its moments of inertia about 3 mutually orthogonal axes are not the same, then we have to worry about those axis systems and write the moments of inertia as Ix, Iy and Iz. Let us see some examples. In the case of water molecule, the first triatomic molecule with the 2 hydrogen atoms and the oxygen atom here, the center of mass is somewhere here. It is on the axis which bisects the 2 hydrogen, that is the hydrogen O hydrogen bond. Therefore, this is half of the bond angle, and if this is the center of mass, this axis, which is also the molecular symmetry axis, is usually called the Z axis. Okay. Then what you have is a y axis which is perpendicular to that, okay, and an x axis which is actually perpendicular to the plane of the screen that you have. So, which we normally write as like that. So, if these are the 3 axes x, y and z, and if the moments of inertia are calculated about these 3 different axes, you would see that the Ix is not the same as Iy and is also different from Iz. Such molecules in which all the 3 moments of inertia, these are principal moments of inertia, we have chosen the axis system such that we worry only about these 3 moments, and these principal moments of inertia which are different lead to characterizing this molecule as an asymmetric top. And other examples of asymmetric top, in fact most molecules are asymmetric tops. Other example is again ozone, in which you have all the 3 oxygen atoms, of which the 1 oxygen atom is connected to the other 2 in a different way. And this is also, I mean, it is identical in symmetry to the water molecule, and you have sulfur dioxide as an example. If you think about this, nitrogen dioxide, nitric, there are many examples of molecules which are asymmetric tops. Now, it is possible that in molecules 2 of the moments of inertia may be equal to one another, but different from the third, and that happens in molecules such as methyl chloride or chloroform, for example, any molecule which has a C3 symmetry. C3 meaning a 3-fold axis about which the molecule has a symmetry. Any such molecule will have 2 of the moments of inertia. In this case, of course, the C, let us take CH3Cl. So, we have CCl bond axis, and then we have the 3 hydrogen atoms which form an equilateral triangle plane. I mean, If you connect that, in the plane of the three atoms will be an equilateral triangle, and such molecules have the moments of inertia about the z axis Iz is different from the moment of inertia about the x axis, which is equal to the moment of inertia about the y axis. And there are two categories here, that the different moment of inertia from the other two which are equal may be less than the other two or greater than the other two. If it is less than the other two, we call that as a prolate symmetric top. If Iz is less than Ix, which is equal to Iy, it is called prolate symmetric top. Typically, such symmetric tops are written or depicted using an ellipsoid of this form. The other, in which the different moment of inertia is actually greater than the two equal moments of inertia, this is called oblate symmetric top. The oblate symmetric top is usually written or depicted like an ellipsoid of this kind. This is of course an ellipse in 2 dimension, but the whole thing is an ellipsoid. The 3 moments of inertia actually become the 3 axis system for drawing the ellipsoid, and this is the one of the axes, and the other 2 axes are like that, perpendicular. If all the 3 moments of inertia are equal, such a molecule is called a spherical top. Now, methane, for example, or the carbon tetrachloride, or carbon tetrachloride, these are examples of spherical tops. That is, it is easy to see that if you draw a cube approximately, okay, and envision the tetrahedral symmetry using the cube. Okay. The tetrahedral symmetry essentially means that the cube has opposite corners of the face occupied by the 4 atoms. So, here is the hydrogen atom. So, if you want this as the carbon, then the face diagonal to that is this. So, if you draw the bond like that and the bond here, and the other 2 face diagonals are these. So, these are the face diagonals in this face, these are the face diagonals in this face, and you can see that they come out, and if you connect all 4 of them, you see that the tetrahedron is actually half the symmetry of a cube or an octahedron. And in this structure, it does not matter to you whether you are looking from the top face or whether you are looking from the side face or this side, etc., because the molecule is identical whichever way you look at it. And therefore, if you draw the 3 mutually perpendicular axes as the axis for the principal moments of inertia, it is seen that the atoms are at the same distance away from each of these axes, and so it is immediately clear that the 3 moments of inertia should be the same. And likewise, for an octahedral molecule, a perfectly octahedral molecule also has all the 3 moments of inertia identical if all the 6 atoms are the same. So, these are 3 different cases that you can think about, and the linear molecule is a special type where 2 moments of inertia are equal and unequal to the third, but unfortunately the third is 0. It is a point mass approximation. Therefore, it is not a spherical top, it is not a symmetric top. The symmetric top has both the moments of inertia non-zero, reasonably big enough for them to be observed in one way or the other. But in the case of a linear molecule, it does not happen. There is only one moment of inertia, 2 of the 2 components are equal, but the third is 0. So, there is a difference in the fundamental classification of the molecular moments, moments of inertia. Now, what happens is the rotational kinetic energy when there are 3 different moments of inertia is given by the angular momentum components in those directions divided by the moments of inertia about that axis j y square by 2 I y plus j z square about by 2 I z. We shall not study the general Hamiltonian and the energy levels of the asymmetric top. If you write this as the operators, then it is 2 I x plus the j y square, the operator for that 2 I y and the j z square by 2 I z. We shall not do that in this course, no. It requires slightly more detailed analysis. So, what we will look at is the case of symmetric tops. For the symmetric top, let us consider the particular case that I x is equal to I y and I z is different from both of them. Therefore, you have the Hamiltonian rotational, which is only the kinetic energy component of the rotational motion, is j x square plus j y square divided by 2 I x, because x and y are the same, and then you have j z square divided by 2 I z. This is the symmetric top Hamiltonian with the operators, and one must know that the angular momentum operators j x and j y do not commute in the sense of in quantum mechanics, and these have a particular commutation relation minus I h bar j z. I use the minus sign because these axes x and y and z are fixed in the molecule, and they are actually rotating and moving with the molecule. They are fixed at the center mass of the molecule, but they are rotating with the molecule. So, these are called body fixed axis systems, and this is different from what you studied in the case of hydrogen atom, where you would have studied that the angular momentum Lx and Ly, the components of the angular momentum, do not commute but give you something like that, and then correspondingly Ly, Lz give you I h bar Lx, and Lz Lx give you, the commutator gives you I h bar Ly, and so on. Whereas for molecular spectroscopy, the components that we have here are such that they have the minus sign. They are called anomalous, they are called anomalous commutation relations. Commutation relations. And what they have is j alpha, j beta is I using some specific notation called a third rank tensor notation, epsilon alpha beta gamma, it is called j gamma. Okay. If you do not know about this, do not worry, all it means is that j x plus comma j y, the commutator is, sorry, that one should be minus I h bar, okay, minus I h bar, and this is j x comma j y is minus I h bar j z, these are operators, and j y j z are operators with the minus I h bar j x, and the third one j z j x is minus I h bar j y. All of them commute with the square of the angular momentum operator, whether you write j x or j y or j z, all of them. That commutator is 0. Therefore, what it means is that in quantum mechanics it is possible in our description of the molecular rotations, it is possible for us to find eigenvalues for operators which commute with each other, and here the operators that commute are the square of the angular momentum and one component of the angular momentum, and usually this component is chosen as the z component or the component in the molecular symmetry axis, which is the highest symmetry axis for any molecule. Given that, therefore, when you write the Hamiltonian for this system, the symmetric top, particularly when you write this as jx square plus jy square by 2ix and jz square by 2iz, you replace this combination by the total angular momentum square minus the z square component, and you write 2ix plus jz square by 2iz. This is the Hamiltonian, which contains the operators j square and jz square, and they of course commute with each other. Therefore, it is possible for us to actually find the solutions to the angular momentum problem by solving the Schrodinger equation h psi is equal to E psi, but there are two operators j and square and jz, and both of these are found to satisfy the property that jz acting on the molecular function gives you a quantum number k h bar psi, and j square on the quantum number on the wave function gives you h bar square j into j plus 1 psi. Therefore, you see that the wave function is simultaneously the eigenfunctions of these two operators. We write this by writing the values, eigenvalues here j and k, and j and k, to denote that the different sets of different eigenfunctions you have, namely k going from minus j plus 1 to plus j. So, there are 2j plus 1 eigenfunctions. This was also mentioned in the last lecture when I talked about the bracket notation jk. These are psi jk or these. So, there are 2j plus 1 eigenfunctions, and this is important because this differentiates the spectroscopy in principle of a symmetric top from that of a linear diatomic molecule. Now, these are the inputs for us to calculate the Hamiltonian on psi jk, and the Hamiltonian is of course h bar square by 2, what we have here is h bar square by 2ix, and the operator j square gives you j into j plus 1, and the operator here, the jz square, gives you h bar square k square and the other term in the Hamiltonian, which is jz square by 2iz, gives you simply h bar square k square by 2iz. All of this being the eigenvalue multiplying the eigenfunction psi jk. This is the quantum mechanical solution. So, the notation that spectroscopists use, or to keep in mind, remember Bj into j plus 1 times Hc as the energy of a diatomic molecule, and now the energy for a polyatomic molecule, which is a symmetric top, has that and some additional terms. Let us call the quantity h by 8 pi square I z c, which comes from this term h bar square by 2 I z. If you call this h c times A, again a wave number, then A will be h by 8 pi square I z c, and so this is A, this will be B. Therefore, the energy level, if you look at it, when you write h psi j k as the energy which is now dependent on the two quantum numbers E j k psi j k, and if this E is therefore given in terms of h c B j into j plus 1 minus k square, that is this term, and then you have the other term which is given as plus h c A k square on psi j k. Okay. So, all I have done is to associate the rotational constant with this term as the old B constant, this one, with the hc, and the rotational constant with the principal moment of inertia along these the symmetry axis as the A constant. So, now we have two constants for this symmetric top, because there are two moments of inertia. Okay. So, if you write the energy divided by hc j k, then this is B j into j plus 1 plus A minus B times k square. Therefore, you see that the energy levels are no longer 2j plus 1 fold degenerate as they were in the case of a linear or a diatomic molecule. The energy levels for a diatomic molecule were the same for all values of k for any given j, and we used this in the last lecture in determining the intensities by saying it's each energy corresponding to a given j is 2j plus 1 fold degenerate. Now, in the case of symmetric top, we see that that is no longer there, the symmetry is now reduced, and what you have is the energy level is now a function of the square of k, and it is of course a bj into j plus 1 with the additional term. Also look at the magnitude of A and B. If you look at it, A is proportional to 1 by Iz, the principal moment of inertia along the symmetry axis, and B is proportional to 1 by Ix, and this Ix and Iy are equal, Iz is different. Therefore, you see if Iz is smaller than Ix and Iy, we said it was a prolate symmetric top. Therefore, for a prolate symmetric top, A is therefore greater than B, because the moment of inertia is smaller than the equal moment of inertia. The unequal one is smaller than the other two moments of inertia which are equal. Therefore, the rotational constants will have the inverse relation. The rotational constant A, which corresponds to the inverse moment of inertia along the symmetry axis, is actually greater than that of the other moments of inertia, namely the rotational constant B. So, this is important. Now, since for any given j we have k going from minus j 2 plus j, we can write this as 0 plus minus 1 plus minus 2 plus minus j k. Therefore, we can write the E j with k is equal to 0 as one energy, and that will be simply B j into j plus 1, because the other term, if you look at it, B j into j plus 1 plus A minus B times k square. So, let us keep that in a corner somewhere. E j k is B j into j plus 1 plus A minus B k square. Let us keep that. This is what we are using to write down for write down the expressions for different energy levels, and when k is 0 you get only that, and when k is plus or minus 1 you get B j into j plus 1 plus A minus B, okay, and so on. So, let us write now the energy levels for j is equal to 1 to start with, which is non-trivial case. Therefore, E 1 0 is 2B, E 1 plus minus 1 is A 2B plus A minus B, 2B plus A minus B, k square is 1, therefore, that is A plus B. And please remember, A is greater than B, therefore, A plus B is greater than 2B. So, if you write the energy level expression, the j is equal to 1, k is equal to 0, which corresponds to 2B, will be slightly lower than the energy level for j is equal to 1 and k is equal to 1. This will be A plus B. The difference here is of course A minus B, which is positive. Okay. Therefore, for a prolate symmetric top, the energy levels actually increase for a given j from k is equal to 0 to k is equal to plus minus 1 to plus minus 2 and plus minus 3 and so on. Therefore, if you write this again now for j is equal to 2 and j is equal to 3, we will write this for 2 or simple examples. This will be 6B when 2 0, 2 is the quantum number for j and 0 is the quantum number for k. So, this will be 6B and 2 plus minus 1 will be, remember, B j into j plus 1 plus A minus B. This is 6B plus A minus B. So, what you have is A plus 5B, and for j is equal to 2 you have 12, and this is of course k squared, therefore, there is 4A. So, what you will get is 12B plus 4 times A minus B, which will give you 4A plus 8B. So, for a symmetric top for any given j, there are j plus 1 energy levels. Okay. The plus 1 is due to the fact that the k is equal to 0 state is non-degenerate, and for all the other states j is equal to 2, this is k is equal to plus minus 2, and that is a maximum. And for j is equal to 3, of course, there will be 4 energy levels corresponding to 3 0, 3 plus minus 1, 3 plus minus 2 and 3 plus minus 3 and so on. This is for prolate symmetric top. For the oblate symmetric top, the energy level expression is still the same. It is E j k, which is B j into j plus 1 plus A minus B k square. But for oblate symmetric top, A is less than B, and therefore, what you see is this term is a negative contribution to the j k is equal to 0 state. Therefore, Ej0 will be the highest among all the energy levels Ej0, Ejk, where k goes from plus minus 1, plus minus 2 to plus minus j. Among all the energy levels, the highest one will be the one with k is equal to 0, because the other term is negative for any value of k. Therefore, the energy levels decrease. Precisely what you see here as an increasing progression of energy levels, you will see the reverse, with the highest level being the 2 0 and the next one being 2 plus minus 1 and the next lower one being 2 0 and so on. So, the relations are inversed. Okay. This is about the symmetric top energy levels. So, in summary, what we have to remember is that Ejk is equal to B j into j plus 1 plus A minus B times k square, and for any given quantum number k, quantum number j, for any given quantum number j, there are j plus 1 levels, j plus 1 levels. So, we shall stop here and take a look at some of the examples of the symmetric top molecules and study the energy level and the transitions in the next half of the lecture. Until then, thank you very much.